vector is eto. That lambda b is a scalar quantity we may taken out. So this is the mapping of C is the GBA. Now come to that how to find out upper and lower of this tensor is derived here. We just going to find out how to find out the magnitude of vector. The magnitude of vector is just the lambda inner product of 2 lambda, and taking the transformation law, we will find the lambda is this one, lambda eto. We find that the lambda cos theta equal to inner product of this and the magnitude of this. It is the just similar to this one. Now I come to that the general transformation. It is the coordinate transformation, general transformation. This is transformation of this one. It is the general coordinate transformation. This is general coordinate transformation. We so if this general coordinate transformation, we if we write this is this way, this then this becomes the coordinate transformation with the usual transformation we get. Now how we find the connection term? The covariant derivatives of a metric tensor is 0. We have written here. Then we write this is the scalar quantity and the covariant derivatives of eto is the just z eto. Now z eto is the derivatives of just term one by one we take, and then this will come eto, this one. Now z eto becomes this one earlier. Now this is the covariant derivative. So this is 0. We always take for any space. The z, this one is the expression of this one. Now taking the rotation x, y, z rotational and then adding, we will get the metric connection. Now taking this, if we take the basis vector, we take one. This is the covariant derivatives of this one, and then taking the cyclic one, adding 2 and subtracting the 1. Adding 2 and subtracting 1, we will get the connection, Libc beta connection. This comes to this one, and that is multiplied by eliminating this one. This one can't. This is the multiplied by the contravariant metric. Then this will become this one. This is the usual Libc beta connection in terms of metric. Now to the transformation law of this one. This is the bar coordinate system. This is equal to this. Now this is the transformation law of this one. Now we take this is the transformation law. This goes to eto this one, and the transformation law of this is this one. They take in the covariant derivatives by 2 terms by simply the differentiation process, one by one, differentiating this from this and keeping this out, and differentiation of this with respect to this, keeping this out. This is the simple way to find out this, and then we will find that this is the if we take the transformation law of this is this one, and if we eliminate EP and EP, and ER is taking R is equal to P, then we can eliminate this one. This is the EQ, and then we take the inverse of this metric, multiplying this metric, we will get the transformation law of this connection term. So this is not a tensor because of this term. This is not follow the tensor transformation law. Now come to geodesic equation. Geodesic equation, abstractly we write that this, abstractly we can write that if we take the vector, we take a vector in this way, that we take the vector like this, same vector, same direction, there is no change, so it is 0. Now it is comes that that it is the component, and we use that lambda is the parameter of this, and this one, and we will find that the will become the geodesic, usual geodesic equation. The earlier is the compact geodesic equation. This is the this type of geodesic equation everyone knows. If we eliminate EC, if we replace B by C, then we can eliminate this easier. This is the geodesic equation. Now come to tensor. Torsion tensor is defined by this one. This is the vector space. 2 T cross T2, another vector space. Now we take, if we take the basis vector, Now we will find the this torsion tensor is anti-symmetric x and y, and if we take the basis argument, now we like to show that it is a tensor. These tensors we can test that it is linear in every slot. This linearity can be checked by addition or multiplication. Now we use the addition. First slot is x plus z. Then we can find out this one. So it is linear in x. If and also in x and y are anti-symmetric, so it is easy to find out the linearity condition in y. Now we take the scalar multiplication of x. It is find that it can be taken out by elaborate calculation is here. This elaborate calculation we have to keep care for our student. That can be that can they may understand it. If we take the basis vector x bar equal to this bar equal to then this tensor can be expressed in this. So this is the structure constant. For coordinate basis, this structure constant is 0, and this is the Libby beta connection. Now Riemann tensor, this is the mapping of our three vector space, cross product three vector space to a vector space. It is defined by this one. Now we can show that it is anti-symmetric in xy and anti-symmetric in xy. So we can write this is x and y replacing x and y. If we take the if it is a tensor, then it must be linear in every slots. Since x and y related by this relation, we should test the linearity for x and y only. Now if for multiplication test is only have done here x. Now we can elaborate a place in place of x. Here we use fx. Now we take the usual calculation. We will find that this is this way to find out if natural way we can find out that f is out, and so it is linear in x. Another second is whether it is test whether it is linear in z. We can find that it is find that we in this way to just a calculation, simple calculation, not hard calculation. We'll find that it is linear in f. Now this is Eto, this is the R expression. So it is linear in Z also. Hence, R x y z is a tensor of type F. This one. Now we find the basic component form. If we take x, y, z as the basis vector, we will find the component of this vector. The component of this vector we can find z. This one, this basis vector, we find replace it here. We will find that this basis vector eto and eto. Now use 2.1 and 2.1 here. Also the commutator law. The commutator law gives the structure constant, and we use the derivative term in 2.1 given here. Now we come that this is this way we can find out the define the tensor. This is the cyclic, this equal to cyclically DBC EA places here. We can find we eliminate EA everything every here. So we will find the tensor here. Component of this tensor basis vector. This is the expression for basis Riemann tensor. It is the usual expression for coordinate system. Now I'm just giving the Ricci tensor. Since this part is the metric part and this is the derivatives part, so we can construct either a with respect to C or a with respect to D here. So here I have construct the a with respect to D here, and with respect to D here, with this will this transformation will become this one. Now this we can express this Riemann tensor in terms of Ricci tensor and metric tensor like this one by substituting this. Now we come to the cyclic identity. This is the general identity. We can take the this is the 0, commutator is 0. The cyclically we write x, y, z, y, z, x, z, x, y. This expression from this expression we will place here, and we take This is the commutator here. These commutators are 0, G is 0, G is 0, and this is commutator. Everything is 0. So this is equal to 0. This is the cyclic identity in general form. If we consider, if we take the x, y, z is the basis vector, then we can express this is this one. Now taking the cyclically, DBC, cyclically, then we will get three expression 6.1, this one, 2, and this 3. Adding this, right hand side will be 0. Then right hand side will become 0. Hence, we will get the cyclic identity like this one. Now, take the Bianchi identity in general form. For Bianchi identity is this one. General form, we will take the all Lie brackets are 0. Do all Lie brackets are 0, we find that taking this one derivatives, one derivatives are taken here. This is the expression like this, and this becomes this one. It is the taken of commutator of this one and this one. This is the first one, and this one is these two one. So now we can write this expression z, x, y cyclically. Z, X, Y cyclically, and then adding them, we will get that this is the commutator using commutator. This commutator 0, this commutator 0, this commutator 0, and this is the cyclic. This is the this commutator, this one, and this one is this commutator, this commutator. This is the Jacobi identity. Jacobi identity always 0. So this is the Bianchi identity in general form. Now we take the coordinate system, geodesic coordinate system, this connection term equal to 0, this expression becomes this one, and then write DCEP derivatives, then taking the derivatives, this one partial derivatives, and then taking the cyclically, CEB cyclically, and then adding, we will get the Bianchi identity in component form, which is the Bianchi construction of tensor in different way. May I have little time? May I have it meet your time? Another.
Sir, you have 5 minutes more.
Okay.
Please.
It is the mapping of this tensor. This is the two-type tensor, the bilinear. This satisfies the bilinear condition. I'm not interested to take this. It is the given here. Now, just come to the most general and see case. It is the basis vector. It is the, I'm not escape this. This is the tensor. I'm just come to the general form here. For general type of tensor, constant of tensor of type RS. It is the most general type. We take the basis of the tensor as a vector space, and this is the basis of the dual vector space. Dual vector means T star. Now we can write here n plus f. This is the maybe this is the basis of the type TRS tensor. This maps the dual vector space TR times a dual vector space to S times a vector space to real field. Now we take that real field. By that we take, if we take the vector from this one, the lambda tilde 1, lambda tilde 2 is from taking the vector from this here, and this is the dual vector. This dual vector from this cross product, we take the vectors mu1, mu2 to mu. There are S number of vectors. This is the vector. We can write this vector as the linear combination of basis vector. Linear combination of basis vector. This is equal to linear combination of basis vector. We will find this one, this like this. So we take that. In particular, if we take the basis vector from the argument, then we will get the Kronecker delta. Kronecker delta, lot of Kronecker delta. This Kronecker delta C1 goes to a Kronecker delta A1, C2, A2, CR, AR, CR, AR, and B1, B1, D1, BS, DS. It is the Kronecker delta we have given here for mapping of this. So if tau belongs to TRS, tensor of type RS, there are a number of component needs n to the power r plus s. The n to the power r plus s component is here. It is defined by that t tau, taking the basis vector in the argument, we will get TA1 to AR, B1 to BS. Now tau of this one, any general vector we have taken, this general vector can be written as the in terms of basis vector. So component can be taken out, and we will take the basis vector. Basis vector give the component. Basis vector is tau one works on the basis vector a1 to as. Now this is the basis vector gives the component this one, and this component is this one. Now using earlier expression, we write this one. This one is the f f of this one. F of this one is this one. So we can we can eliminate both sides the argument this vector these vectors from both sides. Then we can say that tau is the linear combination of this and this basis vector. So we can say that tau is a linear combination of this basis vector. Now we have to find out that these basis vectors are linearly independent, but linearly independent. Now we take this is the linear combination of the basis vector to a vector. This vector. Now take the arguments, the basis vector of like this one uh, on both sides. Argument is taken on both sides. We can write this. This is again these and these are the Kronecker delta. The Kronecker delta goes to Eto and replace this Kronecker delta value. Here we will find that this is equal to 0. This is the coefficient. This is 0 for every C1 to CR, D1 to DR. That means that every one of this coefficient is 0. Hence, it is linearly independent. So thus we have seen that tau belongs to a token expressed as the linear combination of this basis vector, and these basis vector are linearly independent. So they form the basis of this vector. The non-singular transformation of basis vector is like this one. Non-singular transformation like this basis vector. It is the this is the non-coordinate basis. Now taking this coordinate basis, this is the
Sir, please
component
try
method.
to
Okay,
finish.
okay, finish. I'm going to finish here. This is the way to find the transformation law, and this is how we can construct the tensor by using multilinear functionals. I would like to stop here. The references I have taken the two books, taken from two books, but everything from these books not taken everything, but I have taken my own calculation and own theme to introduce here. One of the book is Froster and Nightingale, published in 1979, a short course in general relativity, Longman mathematical text, Barnard Schurz, 1980, Geometric Methods of Mathematical Physics, Cambridge University Press. This book is very important but very tough to understand. Thank you all for giving me the opportunity to present an article. Thank you.
Okay. Thank you, sir, for your nice presentation. We have already received a couple of questions through
Okay.
the chat box. So first of all, we are going to our valuable audience. So please, from our audience, I am give the floor to. Do you have any question, please? Ask some question if you have. From the audience, someone raised your hand, please. The question is, someone has raised your hand. Okay, so now I'm going to our chat box. We have received some question. So, okay, so in the first question is, the question is, functionals are linear at every slot. So in what aspects? Mathematical or geometrical?
It is the
Sir,
mathematical.
repeat this question.
Okay, I understand that. You have shown that
Okay.
all of body, I think, so mathematics person, they have the knowledge, preliminary knowledge in mathematics. I have, you know that in linear algebra, we said that uh, a function is linear when this variable is replaced by some constant into multiplier of this variable. If we take out this constant outside, then it is said to be linear in that slot. Now I am taking that it is linear in every slot. This means that I have here that it is linear. I have used here that linearity condition. I'm going here just it is I am going here that it is the slots here that I am giving here it is linear in x. If it is linear in x, we replace x by fx. If we take f is outside, then we may say that this functional is linear in x variables. If we take y by replaced by gy, then if we can take out the g outside, then we may say that this functional is linear in y. We have also seen that here if we have used that z equal to fz, we have seen you have seen that we have taken that f is outside, so it is linear in z. So it is multilinear means it is linear in every slots. That is, it is linear in x, linear in y, linear in z. Okay, everyone
Okay.
understand?
Okay, sir. Thank you, sir. Uh, so I am requesting from our audience, do you have any more question, please? Okay, sir, please stop your screen share. I'm
Okay,
requesting
thank you.
Professor Ashraful
That-
Islam sir to stop your screen share.
Okay, thank you.
And we are very glad to inform you that Professor Abul Mansur Chaudhuri, sir, ex-director, JN Islam, RCMPS director, and UGC professor already joined with us.
Thank you.
And we already requesting sir to stay with us. And after the scientific session, maybe we will some discussion from sir. Okay, so now uh, uh, a token of appreciation from the Department of Mathematics. So now I would like to request Professor lecturer Erfanul Kobir Chaudhuri, please give a token appreciations to Professor Ashraful Islam sir. And this kind of crest, sir, you will be received this crest later in your
Thank you.
address.
Okay, thank you. Thank you.
Okay. Thank you very much, Irfan. Stop this. So our second talk will be given by Professor Muhammad Jalal Ahmed. So the title of the talk is Application of Mathematical Sciences in Engineering Fields and More. So I'll give some brief description of Professor Jalal Ahmed. Dr. Jalal Ahmed is a professor of mathematics, is currently working, and he did his MPhil in theoretical fluid dynamics from JNI RCMPS, and then he did his master's in computational science from the Memorial University of Newfoundland, Canada. Finally, he was awarded PhD in the field of applied sciences, multi-phase flow analysis in hydrocarbon reservoir using CFD and experimental approaches from the same university, Canada. Dr. Ahmed developed different numerical approaches to study flow through porous media during his research, and he also developed experimental tool to investigate near wellbore flow phenomena considering turbulent flow. and his research interests are multi-phase flow electrophoresia, numerical techniques in the field of CFD, and designing experimental tools for fluid flow. So I'm requesting Professor Jalal Ahmed to deliver his lecture, and you are allowed to finish your lecture 40 minutes, please. Jalal Ahmed.
Uh,
Professor Jalal, please share your screen. Is it okay? Okay, thank you.
Thank you, Professor Dr. Amanullah, to invite me for a talk, and I'm glad to I'm glad to present a talk in this seminar. Especially, this seminar is organized to celebrate the International Mathematics Day by the Department of Mathematics, University of Chittagong. I'd like to give my greetings to all of my respected teachers in the Department of Mathematics, and also who are also retired, especially Dr. Dr. Muhammad Musliuddin Ahmed, Dr. Abul Mansur Chaudhary, and Dr. Ganesh Chandra Rai, Dr. Ashraful Islam, Dr. Neil Ratan Bhattacharjee, Dr. Nur Nahar Begum, and Dr. Toki Bhattacharjee. And today also I remember our respected teacher, Professor Shafiul Alam Tarabdar, who was died due to COVID-19. So today my title already mentioned, and also thanks Dr. Amanullah to introduce me so highly. Today the title, Application of Mathematical Science in Engineering Field and Mode. That means where we can apply mathematics. So I would like to start first using the definition of mathematics. So there are different definition in the mathematics you can find in the literature, but I found, and I think this could be a nice definition. Mathematics is a universal language by which we can solve our real life problem. So if you know the mathematics, if you understand the mathematics, so it is not impossible to solve any problem. So sometimes I say, using funny, if you want to get married, so you are in a problem, so use your mathematical analysis, then you will be success. Anyway, so the application of mathematics in everyday life problems. Here is some example. These are not limited, but there is some I mentioned. So making a routine budget. In the routine budget, we have to use mathematical knowledge, construction and manufacturing industry. So if someone are very good at in mathematics, so that can help them to understand and easily solve the construction and manufacturing problem. So similarly, in interior design and fashion design, we need this mathematical idea. And automobile and aerodynamics, this is a very big industry in the world. So if someone has the mathematics, they have the full demand. Similarly, in cybersecurity, computational computer application, even in weather forecasting, oceanography. So not only that, science faculty, in business faculty, banking, insurance, marketing, and planning. So I had got a chance to attend a workshop in Montreal, 2018 probably. No, 2017. 2017. In that workshop, we have to develop some mathematical model for the insurance company. That is called optimization. That is the our Dr. Mustafa Rizvi is working on that field, and also our Professor Ganesh Chandra Rai's field. Now, in mathematical, medical science and sports, in the medical science and sport, we see the CT scan, we see the X-ray in the film, but background, the software used in the computer, that is fully depend on the mathematical knowledge. Even in music and dance, if you someone have a good idea about the mathematical function, I think he could be the good dancer and musician. Even cooking and baking. So far, I remember when I went for my higher study in Canada, I was unable to cook because I don't know the ratio, how much ratio for the cooking I have to put, so that I can get a tasty food. So by doing and learning, so finally I became expert. So sometimes my wife says, so you are good cooker than me. Anyway, whatever I'm saying, even in cooking, if your ratio is good, so you are a good cooker. So you are a good cook. So in that case, mathematics is essential for our everyday life. Now, here is some figure, the beauty of mathematics. So beautiful dance moves. Here is some function you see here. So if someone knows and someone have the idea of this function, mathematical function in their mind, so I believe they could become a good dancer within a short time. Now, in even engineering, so this is a y equal to x squared, very simple function. So just I'm showing this in simply way. So in this building a hanging bridge, so if we need this kind of idea of mathematical idea. Now this is called Batman. So Batman in Bengali we say Bandhur, right? So if you know the mathematics, so you can draw a Batman in your function. So butterfly, this is a butterfly function. So if you know the mathematics very well, so you can draw a butterfly. Now, the application of Fibonacci number and some parametric equation. In the first one, the application of Fibonacci number, I collected just from yesterday in the Google. And the second figure says Rose function. That means that it is a parametric function, r equal to a sin theta and r equal to a cos theta. If n is an odd number, then we get like this rows, and in the C, if n is a rational number, then we can get this kind of flower shape. If n is irrational number, so how beautifully you can see. If it has irrational number, so it looks like very difficult, but it's not that difficult if you use the mathematics. Now this is the fractal leaf. In Bengali we call deki shak, deki pata in Bengali. The first one in the figure A, this is drawn using the computation, very simple computation in MATLAB. And the second one is the real figure. So you see how mathematics can draw, mathematics can analyze the real beauty of the nature. If you go a little higher, now figure A, shows the hurricane of satellite capture hurricane. In the figure B, this is the simulated in the using the computer. So if we know the mathematics, then we can simulate this kind of hurricane in our computer, and then we can predict in advance what could be the strongest and how it could be, and what we can take the necessary step to avoid our disaster. Finally, you see, I think everybody knows this one. This is a picture of a hand drawing picture of Einstein, but this is not hand drawing. This was drawn using some mathematical parametric equation I just mentioned here. Using this equation, so Einstein in the two-dimensional graph. So finally, mathematics using computer. So in the computer, the background, you have to use the computer. Today, computer scientists believe that computer is the second God, because using the computer, there is nothing you can handle. So this figure tells computational science is common in all the field of applied science and applicable science. So now I'm going to my research, wasting time, mathematics in oil industry. So my interest to use the mathematical knowledge in the oil industry, because most of the oil engineer or engineer, they have they know the mathematics, but they fear about the mathematics because this sometimes become hard for them. So in the figure, what is in this figure? If you see, there is some. If I use mine, is it visible for you?
Yeah, we can hear you.
It's okay.
No, is it visible for you? Okay,
Yeah,
so
yeah,
it's
we can
visible.
see it.
Yes.
We can see it clearly. Nice.
Yeah. Okay. Okay. So now this is the extracting the oil. So we can extract the oil from this point. Now, this length could be couple of kilometers. Couple of kilometers. That means if this is in Chittagong, this could be in Dhaka. This point could be Dhaka. So we just make a hole, drill a hole to extract the oil, and becomes it horizontal. First it goes to vertical, and then it goes to horizontally from Chittagong to Dhaka. So we can extract hydrocarbon, that means oil or gas, from one point that is situated far away from the extracting point. So this is a very complicated. There is a lot of phenomena shown in here. Okay. So in this point, so if you see here in the oil industry, when first oil recovery can be done using the natural pressure. After natural pressure decline, then we have to inject some. We have to use some technique. So CO2 injection is another approach. If you inject the CO2 into the underground in the one point of the reservoir, then oil will produce in the other point. This is very complicated, showing in a simple figure. It's easy. So another way, so in nowadays, in the air, we have a huge carbon dioxide. So it comes from different production site. So this is another headache for the industrial, for the environmental scientist, how we can reduce carbon dioxide from our environment. So they this is the idea. You have to collect the carbon dioxide, and then you have to reserve in the underground using the carbon dioxide injection, and then oil will be production. That means you can collect the carbon dioxide and inject into the underground reservoir, then you will get the more oil. So two-way benefited. Now I am going to show another technique, another idea about the grid generation. Why we need the grid generation? In the computational mathematics or computational simulation or computational science, we need to have the grid generation. Grid generation, you know, are familiar in the numerical analysis. So this one is the whole world. So we have divided in some grid, and this is the a very simple turbulent jet. This is the simple turbulent jet with the grid. Grid means the 2 point, this and this part, and this called grid size. Okay. So to do all these things, that is not easy. So we have some scientific challenges. What are that? We have a theoretical challenge, we have modeling challenge. So in the theoretical challenge, if I consider oil reservoir simulation, so oil reservoir is not a very simple, it is complex in nature by itself. So, and also after long-term production, the properties of the reservoir changes. And because the production parameter changes, so your forecasting will be change. You do consider that one. And the modeling change in the reservoir and its fluid have different characteristics. That means pressure, temperature, permeability, porosity, viscosity, density, all these parameters you have to take into consideration. And also flow region. There is in the reservoir, there is this not as like a river, then you will get the oil from the river. So there is some region undamaged, that means there is no damage, and there is some perforated tunnel, that means there is some area that can be treated as a canal, and there is some other area that are fully you can consider as like a rock. There is no way to pass the oil, but there is some poor scale. If you consider in the poor scale, there is some path into the rock so that fluid can pass through the rock. And also boundary condition, because I mentioned here 3 regions. One is undamaged region, one is perforated tunnel, and another was well bore. For simplicity, I have been shown 3 regions. In 3 regions, I have 3 different boundary conditions. So when you do the simulation, you have to consider all this boundary condition for the different region in one simulation. And also mass is another important thing. When we do the simulation, mass conservation, mass is conserved or not. If mass conserved, then your system is well defined. If not, then your system is not well defined. That means something is wrong. Now in computation challenges, now is computational changes in the computer. Usually I am using here Navier-Stokes equation, but in the oil industry they have to they used to use Darcy's equation, which is very simple. This is very simple, but this has some limitation. This is the simplified equation, so it cannot be cover all the features of the reservoir. Anyway, this is the one challenge. What is the other challenge? Size of the reservoir. It could be the order of kilometer. That means some order of kilometer. Here's an example. In one oil field in Canada, it has a production area 180 kilometer square. In China, there is one reservoir which is length about 25 kilometer by 12 kilometer. Okay, now come to the point. What is the challenge here? For a typical reservoir, suppose we have a reservoir which is 10 kilometer width and 10 kilometer length and 10 meter depth, sorry, 100 meter depth. Now, if I consider delta x equal to 1 micrometer, why you have to consider 1 micrometer? Because this research says flow through porous media occur in micrometer. So if my delta x is 1 micrometer, how many grid point I need for this one? I need this grid point, and for this one I need this grid point, and for this one I need this grid point. And what could be the memory for this grid point? 10 to the power 6 terabyte. That means for one simulation I need computer memory for 10 to the power 6 terabyte for one simulation. So one simulation is not sufficient for understanding of the behavior of the reservoir flow. Now, if I go for little higher, then I may consider this grid point. If I consider this grid point, then what will be? Then in that case, oh sorry, first time for this case, I have the grid point, I have the memory this one. For this one, I have the memory this one, 10 to the power 6, and for other one, 10 to the power 15. So what we should do? What is the medicine? What is the prescription for this kind of simulation? How we can get rid of this? So computation model. Okay. So there is some treatment, some prescription. I am not mentioning here, but there is some prescription. This could be, it can be called representative elementary volume area, like this. So now if I go, now I am going to experimental development. Being a mathematician, so what we are doing here, we are developing a reservoir. If you see here, this is the reservoir, but this cannot be a reservoir. In the lab, we made a reservoir which could be the image of reservoir, real reservoir. That means the upscaling. So this is the lab scale of a reservoir. So, and also we made some sample. This sample is made in the lab, and this is collected from the real field, and then we make a hole here to consider as a production hole. Now, after that, if I develop experimental tool to understand the reservoir flow, so before making it public, so I need to have validate it. So there is some process to validate such kind of tool development. So I have validate this one here, and the validation result is accepted. And also after when I do the experiment preliminary, so I validate that setup. Now this also setup is done using for the pressure drop. What is the pressure drop? Pressure drop means when the production is underway, the pressure of a reservoir decline gradually. So that means pressure is when production time is increasing, then production is declining. Because pressure declining. So pressure declining means we have the production. So production is taken, so pressure is declining gradually, because there is no because of the storage of the reservoir, pressure is declining. So this is the mathematical algorithm we have developed. So now we also verified our mathematical simulation model here, numerical algorithm. So if you see, this is the time. This is the time, a small time. This is the larger time. So when time is larger, so flow rate is, pressure is declining, and the flow rate increases due to increasing the time. That means which is the word called IPR curve, which is very important to analyze the reservoir simulation for the reservoir analysis. This is another also verification for the different flow rate. If flow rate increases, and also how pressure drop affecting due to the radial distance. So what is the radial distance? If I go back here, this is the radial distance. So I have the production hole here. So this is the radial distance. This is the radial distance because this is the radius, circular cylinder. Now this is the pressure contour I am showing. Excuse me. For the three different flow rate. If time changes and also pressure is changing, how? So, but looking this figure is difficult to understand how pressure is changing. So I have to analyze this pressure drop using the analyzing the result. So I analyze here. If I zoom in here, so it is visible how pressure is going. Then now the next project that I said we have oil production area, oil bore, and stone, and then reservoir area. That means undamaged zone. So this is one zone, this is one zone, and this is another zone. So I have a three zone. So flow condition in three different zones is different. Boundary conditions are different. So to get a real picture, to understand the real flow, so we have to connect all these three regions in one simulation. So we have to try it, that one. So if you see in the previous figure, we don't have this one. Now we have included that one. So by this way, this time, what is the skin zone? Skin zone means damage zone. Why damage is occurring? When we drill the hole using the drilling technique, so surrounding area get damaged. So that is called the skin zone. In other word, damage zone. So we consider in this figure, we have shown the three component, but we did not consider skin zone. We just considered there is no damage. That means undamaged. Now, in the next figure, we include the skin zone here. If we include the skin zone, then our analyzing the data, analyzing the simulation, have the understanding. But here we don't have it. So what is the difference? Without skin, there is no decline of the pressure. And we consider skin zone, then we have the decline of the pressure here. It's suddenly dropped. So that is the main thing, to include all these three regions in one simulation. So in this figure, we also include different pressure control for the skin zone and without skin and including the skin. How it's affecting the flow using pressure control plot. We have analyzed this pressure control in this figure. Now we understand. We try to do some different simulation how flow rate affecting the pressure drop with time, real distance, and with time. In the next one, so we include a lantern phase model to understand multi-phase flow in porous media. So what is, suppose we have one phase fluid here, that means one kind of density and viscosity. So we have another fluid here, density and viscosity is different. So there is a region of two fluid to understanding the behavior. This is very important in oil reservoir industry, because when we are extracting oil, so the phase of the reservoir oil changes.
Dr. Jalal, please, you have 5 minutes more.
Okay, I need to finish. Thank you. So using this simulation, so we have to consider a bubble here. So using this one, so for the different grid size, so we try to plot it. So different grids, when we use the different grid size, so we see how it's affecting the grid size here. Now we simulate some result to match with the experimental. These are the experimental result published paper in here. This one and this one. This one is the experimental, and these are the experimental. These are the simulation. This is our current simulation, current study, and this is the using porous media. Then in the beginning, I said there is another challenge of mass conservation. So in phase field method, phase field simulation. So we check that one when there is no phase field. So mass is conserved fully, and we include the phase field in between our simulation. Here is some deviation. Finally, we have the mass is conserved. So this could be some numerical error or some numerical technical error or some other error. So anyway, finally we have a mass conserved. Now this is another interesting simulation we have done. The first one is actually occurring like this. So when you are extracting the oil, so most of the oil is not coming. So end of the day, you are getting this amount of oil. So you are not getting all the oil. So if we develop a technique to understand the simulation, how we can get all the oil. So if we use our technique, then we see all the oil coming here. So we are not leaving any oil inside the reservoir. Okay, now what is the next? So if you see some simulation if you go to the market, you will see different types of vehicle, different types of car, and so to design different model and different shape of the car, you need to understand the around the car. In that case, you need to understand computer. You need to understand mathematics. If you have good mathematical knowledge, you will be the expert on that field. Similarly, in the aerodynamics. So now, current and future project. Now, development of numerical algorithm to better understanding of near wellbore reserve. This is one current project under my research group. Development of numerical algorithm to analyze flow behavior around bridge pier. So, new look of blood flow through arterial vein. Prediction of total sediment transport into different rivers of Bangladesh. Invention of new environmental friendly drilling fluid for oil industry. All this current and future project under my research group. So if anyone interested to do MPhil and PhD, you are very welcome. Thank you.
Thank you very much, Jalal Ahmed. So now I am searching some question from our valuable audience. So please, do you have any question related to this talk? From the audience, I'm searching some. If you have any question or any inquiry related to his talk, you may ask.
Sir, I have some questions.
Okay, please give your identity and then ask your question. Your name, please.
I'm M. Abdullah Mahabub from Kumilla University.
Oh, Mahabub, please.
Thank you, Dr. M. Jalal, sir, for nice presentation and a real life application of the mathematics. I have several questions. The first question is about the reservoir. What kind of reservoir you have taken? It's a conventional or unconventional reservoir?
This is a convention. Conventional reservoir.
Conventional reservoir. So in the reservoir, we have only one medium, matrix or fracture or bugs. It could be anything.
Okay. So fracture reservoir. So now you see. So if you see this, is it visible? This figure?
Yeah. It's okay. A multi-level hydraulic fracture wellbore, right?
Yes. Yeah. So there is some fracture, right?
Yeah.
So my research focus is not on that one. My research focus is okay. So I'm showing you. I'm showing here. Okay, my research focus not here, right?
Yeah.
My research focus is on here. Do you understand? So yeah. I am not considering fracture here. Just I'm considering when you drill the hole, so you damage some area, right? Yeah. So this area is undamaged. This area is undamaged, right? So and this is damaged. The black dot are damaged. So this is the hole. So I am concentrate on this area, not the fracture or unfracture. There could be another project for fractured porous media. So and you consider fracture porous media, then there could be hydraulic fracture or natural fracture. This could be this kind of question will arise. Okay.
Yeah. So you are basically.
Did I answer you?
Yeah. You are basically simulating only the multi-fracture hydraulic wellbore, right? Only fracturing the fluid flow medium, not the porous medium, or the fracture or the reservoir medium.
No, I said to you, I am not considering the fracture or unfractured zone, right?
Yeah. But are you considering the reservoir, the simulating the reservoir, or only the wellbore, only the wellbore region?
No. So okay. So I have to draw for you So I have to draw for you.
Because the Navier-Stokes equation only works for the free flow region, right? So
Sorry, can you repeat again what you say?
yeah.
Please.
My question is the reservoir is full of the porous media or matrix of fracture. So the Navier-Stokes equation only works for the free flow media. Like there is no like porous media.
Yes, Abdullah. Yes, Abdullah Mahbub. Yes, Abdul Mahbub. This is the beauty of using Navier-Stokes equation in porous media. That means the reservoir. People believe that Navier-Stokes equation is not valid in the porous media, in the reservoir. So we are using Navier-Stokes equation in the reservoir to capturing all the quantity in the equation, in the Darcy equation.
Yeah.
People believe that Darcy's equation is valid in reservoir or porous media.
Yeah.
But that is the very simple. But Navier-Stokes equation is generalized. We are considering, you can consider all the features of the Darcy's equation in the Navier-Stokes equation. So Navier-Stokes equation could be the general.
Yeah.
Do you understand my
Okay.
question?
So
Okay, thank you very much.
yeah. So reservoir have the permeability or porosity or compressibility, but
Exactly.
don't have such kind of constants.
What's that?
I mean, in the Navier-Stokes equation, we don't have like permeability, because in the simulation I see you have taken the millidarcy. Permeability is millidarcy, 100 millidarcy to 250 millidarcy. So in the Navier-Stokes equation, we don't have the permeability or porosity constant in the Navier-Stokes equation.
We do have.
Yeah, in this project, I can see you have taken 250 millidarcy.
But because I didn't show any equation here.
Yeah.
Because of time limitation, I didn't show any equation here. So if you Google Google my paper, then you will see. Or if you're interested, I can send you the full paper so that you can understand and you can look at the how I included all the features of reservoir in Navier-Stokes equation. Okay.
I have last question. Yeah, what kind of scheme you have used? Like it's a finite difference or finite element or finite volume?
Yeah, this is my question also. What kind of numerical scheme you are using?
I have been used finite element.
Okay. So, Dr. Jara, I have one more question. You said
Go ahead,
the
please.
mass is conserved. So, what about momentum and energy? So, is it need to check the conservation of momentum and energy? You said that if the mass is conserved, then this is everything is fine to check your numerical simulation. So, do you need to check the momentum and energy? The conservation,
because first thing, I am not considering energy equation here.
Yeah.
So right.
Yeah.
So energy conservation is not my headache. So momentum conservation is related to the pressure, right? Okay. So I am analyzing the pressure. So that I did not consider the conservation of the pressure, but why I focus on the conservation of mass? Because in the oil industry, suppose this is the initial condition, right? Initial mass. So when a flow is coming here this is the outlet, this is the inlet. When the flow or fluid comes here at the end of the output side, so I have a mass m here. Now I have to check, do I have a mass m here or is less than m? So if this m and this m is same, so I can say that mass conserved. So my technique and my simulation very much correct.
Okay.
So that's why we consider the mass conservation analysis here.
Okay, thank you. So if
You are welcome.
our audience, if you have any more question, you may personally contact with Mr. Jalal. So we are very grateful to you for your nice presentation. So please, your screen share of this screen share, please. So now,
If any, if from audience, if anyone can want to contact, so my email at cu.se.bd, jalal.math@cu.se.bd.
okay,
You can contact through. Thank you
okay,
very much.
thank you, thank you. So
Thank you all.
now a token of appreciation from our department. So now I'm requesting Mr. Erfanul Kobir Choudhury to give this token of appreciation to Dr. Jalal. So you will get this crest of its hard copy from your address or from your department. Thank you very much for your nice presentation. So
Thank you for the gift, but I didn't accept.
why?
I don't wish like this. Thank you.
Oh, okay, it's okay. So we are much waited for Mustafa Rizvi. He's from Australia, and we're requesting him to give a lecture, and he's cordially accept our request. So now I'm requesting to give the lecture on the scalarization approach to generate the Pareto front of multi-objective optimization problem by Dr. Mustafa Rizvi, and currently he's a visiting research fellow, University of South Australia. And I'm giving a brief description of Professor Rizvi. Mohammad Mustafa Rizvi is an associate professor of the Department of Mathematics, University of Chittagong. He is currently pursuing the postdoctoral research at the famed University of South Australia. He has completed his MPhil degree under the supervision of our esteemed professor, Professor Jawan Nazrul Islam of the JNIRCMPS, and completed his PhD at the University of South Australia. His research mainly focuses on optimization, optimal control, multi-objective optimization, and operation research. Now, I'm requesting Mustafa Rizvi to give his lecture, please.
And thank you, Dr. Aman. Can you hear me?
Yeah, it's clear.
Oh, okay. Can you see me? I'm sharing my slide there.
Yeah, it's clear. It's clear.
Okay, that's great. Thank you. Thank you, Dr. Aman. Good afternoon, all. I'd like to thank you, the organizing committee, to arrange this seminar and give me the opportunity to present my research work. And also, I'd like to thank you, our respective respectful teachers, Professor Dr. Abul Mansur Chaudhary, Professor Musliuddin sir, and Professor Ganesh Chandra Rai sir, and Professor Ashraf Islam sir, and all other teachers and colleagues and students. Thank you for your attention and for giving time to attend this session. So I'm Mustafa Rizvi. I've been working as an associate professor at the Department of Mathematics, University of Chittagong, and my specialization area is optimization. Today's talk is part of my research work. The title of my talk is a scalarization approach to generate the Pareto fronts of multi-objective optimization problems. So this is actually the joint research work with Rahina Burachik and Yalchin Kar, who are my actually PhD supervisors. Later, I collaborate with those and produce a lot of impactful research. So here, let's start with the topic that I actually covered, multi-objective optimization problems. So I want to discuss or give you the definition of multi-objective optimization problem first. So as you know that we are familiar with linear programming and nonlinear programming. Usually what we have a single objective optimization, a single objectives in the problem. So subject to some constraints. Here we consider more than objectives there. So suppose that in this model, I have a L number of objectives. So we have a finite number of objectives subject to some constraints. So constraints maybe you can ignore. In that case, you can call them multi-objective. unconstrained optimization problem. So this is here in my model, I consider the constraint, because when you consider the problem is more complicated there, when you consider constraints here. So I refer, this is my original problem. Suppose that I have that L number of objective functions subject to the constraints. So I'll call them P, and I refer them always in doing my talk as an original problem. Now, when I consider these functions, I assume that all functions, objective functions, are strictly positive. So you may thought that it's a very strong condition. So we can ignore for the time being, say that if we see that somewhere is a negative, so we add a big reference point so that we can force them to make it positive there. And all constraints, they are real valued functions. So it's a Rn to R. And capital X, throughout my talks, I consider capital X is a feasible set. So the definition of feasible set, any points which satisfies all constraints, we call a feasible set. Now, another thing we need that we call that objective feasible space. That's actually, we transform this feasible set into the objective space. For example, so if we have two objectives there, so we transform all our solution into objective space. So in that case, my X coordinates would be F1 and the Y coordinates would be the F2. Now, this is the structure of the model. So multi-objective optimization problem actually has a bunch of applications there. So one of the, so here I listed few of them. Say that first one, you can see that the water pump from the ground. So that's the water allocation problem. So sometimes we need to pump water from the ground level and we allocate this to the crops. So our objective was, objective is to maximize net returns or maximize profit. At the same time, we need to look at that minimization of the deficit of the environmental flow, because we can't produce or we can't pump enough water from the ground level. It can affect our environmental flow. So we have two objectives here. One is to maximize our profit, at the same time minimize the deficit of environmental flow. So another applications, you can put it into a reverse logistic system. So reverse logistic system is a system, something like that. You sell some, say that some products there, say that maybe car, maybe tank, maybe some physical goods. So that after sometimes it may be required repair. So again, you repair it, again, you sell it. So these actually minimize the environmental flow. So the whole process, in the whole process, our intention is to minimize the holding cost. At the same time, we look at, again, the environmental situations, say that we try to minimize energy consumed in the productions, or we try to minimize greenhouse gas emissions during the process. So again, we have more than one objective involved in these problems. When we say that more than one objective involves, we call that multi-objective optimization problems. So another applications you may find, there are actually a lot of applications in presently people's working on UAV. So UAV is an unmanned aerial vehicle. So it's one of the applications I can say you that we always try to communicate with the UAV from the base points here. So in case we try to always maximize network connection level, at the same time minimize the confidence levels of connectivity. So more than one objective involves in this area. Again, you can form a multi-objective optimization problem. So these are only few applications that I present in here. At the end also, I'll show you another applications we actually put it into the rocket injector design problem. So very interesting topic. So now how you operate this, how you solve these multi-objective optimization problems. Usually what happens when you have a single objective, so what do? We have a point that satisfies the constant, we call that feasible point. Then we have many feasible points we can. Then we optimize our objective functions. So optimize objective function, those points which optimize, those feasible points which optimize the objective functions, we call that optimal solutions. That solution is called an optimal solution. So when you consider the multi-objectives, the definition of optimality is too narrow. So it can't apply because it's quite impossible to minimize all the objective functions simultaneously there. So in that case, we need a broader type of definitions, which we call that efficient point and weak efficient points. Now, what's the definition of efficient points? It say that if you claim that some point is efficient points, then the definition is that we'll say that, okay, we will not find any x in the feasible set so that that point is clearly dominated with the points that we are claiming that efficient points. For example, let's take an example, then you can see understand the definition. The definition say that I can choose 2 points here, 2, 3, and 1, 4. So remember that these are the value for objective function. Say that 2 is a value for f1, 3 is a value for f2. Similarly, 1 is a value for f1, 4 is a value for f2. Now, if you claim that 2, 3 is the efficient point, then we will not find any x such that this point is clearly dominated. So if you look at these 2 points, what happened? 1 is less than 2. So it means that 2 is, when you compare x coordinates, say that 2 is dominating. But on the other way, when you consider the y values in here, the y coordinates in here, the opposite is dominating there. So no point is dominating to each other. In fact, we can claim that both points are efficient points. So the definitions say that we will not find any x in capital X such that this condition is hold for every I, and for some I, that should be the opposite. So here you say that 2 is bigger than 1. However, the other objective, which is bigger than for the other cases there. So this is called the efficient points. In other sense, you can call them, say they are non-dominated points there. Now, another definitions we frequently use, that's called a weak efficient point. Weak efficient point is a slight, you see that relaxing there, the conditions that say that we can call any point as a weak efficient point, which then there is no x such that in the feasible region, so that is clearly dominated. So it means that if you again choose these 2 points there, so one of the points they are equal, but other points still they're dominating. Say that second point 4 is bigger than 3. So one can claim that these 1, 4 is clearly dominated with 1 and 3. So when you call that weak efficient, so we are relaxing some strong conditions there. We can say that, okay, we can consider this guy as well there, because one of the is not clearly dominated, but some portion is dominated. However, we can ignore that. Okay, so, but here you can look at that. This is these 2 points here. 1, 3 is the efficient points, but the other way, the 1 is not efficient because definition doesn't hold here. Now, at the same time, I can say that I can build a relation here. So every efficient points are weak efficient point, but the converse is not true there. So this is the relations usually it holds there, because weak efficient point definition is more general than efficient points. Now, another word we use, we call it Pareto front. Pareto front actually is a set of all weak efficient points. So you collect all weak efficient points. So when you collect all efficient point is a subset of weak efficient points. So at the end, set of all efficient points, we put some name, we call that is a Pareto front. So that's the definitions we just need to put in there instead of definition of optimality there. Then the question is how you can solve these multi-objective optimization problems. Is there any special procedure, or you can extend the versions that, or the algorithm that we use in single objective optimization problem? So that's a very good question here. So what do we do actually when we say that scalarization approach? So we have original problems. As I say that I call these at P by P, and we have a L number of objective functions. For the time being, just ignore that, say that we have 2 objective functions there. So that's our original problems. Now what you can do? We'll try to add some parameters with these 2 objective functions. At the end, we'll put some kind of trick inside there. The intention is to transform the 2 objective into a single objective optimizations. Once you're done to original problems, which was a 2 objective optimization problems, to transform to single objectives, we call that scalarization approach there. So in that case, you have to be careful in here, because you need to put a relation between that original solution and the new auxiliary problem. so that suppose that I transform original problem to the original problem to an auxiliary problem, then I need to establish relations that solution of auxiliary problem is also a solution of original problem, or the vice versa. So there are a couple of existing famous scalation approach, usually in the scientific community, people often using there. One of the approaches is called a Pascalotti approach. Is also called a goal attainment method. The method actually very popular methods. So here again, as I say that, you see that if you see the constraints substitute the constraint in here, in my cursor there, all the objective function force to the constraints, and our original problem, it was a multiple objectives there. Now, instead of objectives, we set some scalar items there, subject to the set scalar items, the constraints there. So what do? We solve these auxiliary problems, then we can get problems. If that solution also the solution of the original problems. Now you need to establish that either theoretically or numerically there. Now here you see that W called a parameter. In Jalal lecture, Professor Jalal, in his lecture, he mentioned that we need to put some parameters into the algorithms. We call it. So in our algorithms, we need to provide these W actually is a parameters, but there are structure to choose these parameters. Each of the parameters should be still bigger than 0, but the sum of all parameters should be equals to 1. So when we call these parameters, actually I put a name there. I'll call that grid points there. So we need to generate these grid points. There are some criteria to generate these grid points. It's not like that you choose some W and W, then you put algorithms. So you have some criteria to set these parameters, to provide these parameters into the algorithms. Then you need to solve these auxiliary problems. So this is a very famous existing scalation approach is introduced in 1984 by Pascalotti and Serafini. And this is also called a goal attainment method. So anyone, if you sorry, can you please mute your microphone? Okay, so now here what happened, if you look at the MATLAB, you will see that they set actually these algorithm in MATLAB. So they build some solver. Inside the solver, they have a special algorithm which actually convey these algorithm, which is goal attainment methods. So as I say, that is introduced in 1984. Another very popular methods is the NBI techniques. People often say that NBI techniques is actually introduced by Das and Dennis. Again, what's the difference between Das and Dennis and Pascalotti? You see that all are the same. The only difference in the inequalities. So he just ignored these inequalities. He's just, instead of inequalities, he's just put equalities there. And he extended Pascalotti-Serafini approach. And in 1998, he introduced, or he proposed this new scalation approach. So this is very effective and works well when the Pareto front, as I say, that set of all the front that consists all weak efficient points, we call the Pareto front. So when the Pareto front is connected, it means that there is no gap inside the Pareto front, then these Das and Dennis actually works well. And recently, recently means actually 2014, there's another scalation approach. This is also very popular nowadays in scientific community. So we call that weighted constant approach. So here what we do, suppose that we have two objectives. We just force one objective in the objective functions, and other objective we force to the constraints there. So here K is a number. So suppose that we have L number of objectives. So we consider one objective, which a kth objective is the objective functions, force other objective into the constraints, then we convert the original problem into this single objective optimization problem. So in that case, how many Ks we have? We have L number of Ks. So in our original problems, we have the one problems. Now we convert into auxiliary problems, but how many? We have K number of sub problems there. These auxiliary problems all depends on number of objectives. Suppose that in the original functions, or original problems, we have only two objective functions, then the sub problem would be 2. So, and in that case, consider one F1 as objectives, force F2 into the constraints, or F2 is an objective, force other observation function into the constraints. So this scalation approach actually appeared in the Journal of Optimization and Theory Application. This is one of my research work. It's published in 2014, and actually is now a very popular scalation approaches. If you just look at the Google citations, until now it's had 56 Google citations so far, and people around the world actually try to use that. And one of the evidence that recently the algorithms or the escalation approach, actually they included in a book published called Non-Convex Multi-Objective Optimizations by an eminent professor, Penham Pardalos. So if you just Google that, Penham Pardalos, he's an eminent specialist in optimization. He's a professor of University of Florida. Recently his books, he covered actually 3 escalation approaches. So one of the escalation approaches that we actually proposed in 2014. So today, my talk is not covering this escalation approach, because still we are working on this escalation approach. Very soon we will publish another paper from Elsevier, which actually the mixed integer version or integer version of the escalation approach. So we are waiting soon, let's say. Now today I'll cover the another escalation approach that we propose that is also very effective to solve multi-objective optimization problems. So here what we have, we choose some parameters. First, we have a feasible set capital X. Then we'll fix some, or we'll choose some X tilde from the feasible set. These X tilde should be into the feasible set. And we'll choose parameters. We'll choose parameters dW in W. So remember that W is some kind of grids. Before I actually introduce, I present here 3 escalation approaches. So no one actually set conditions on the grids. They say that any grids would be fine. But here we set a special condition. So we say that, look, any point X hat into the feasible set and W prepared in such a way so that this condition holds. At a glance, again, you can say that I put more conditions here. These would be more stronger than the previous one. But in the algorithms, actually, how you implement these conditions, that's the important. If you see that the implementation of the condition is very easy, then we ignore that because there's easy to implement there. Sometimes if you put conditions there, it's not easy to implement into the in the algorithms. Then then that's the scary things doing the algorithms. So what we did here, again, these times, again, we say that consider one objective functions as objectives, force other objective function into the constraints. So when you force other objective function into the constraints, these times, right-hand side, you see that because you choose this X set before the algorithms, before choosing this auxiliary, or before preparing these auxiliary problems. So when you provide this X set into the functions, definitely these right-hand side of the inequalities would be the constant terms. So in a sense, think about that, y less than equals to 4. So it's a kind of straight line, which is parallel to x-axis. Okay, so similarly, so on the vice versa. So if I consider F2 as the objectives and force F1 into the constant, so F1 means that just compare with x less than equals to something, some constants. So is a parallel to y-axis. So these are the constant actually works. So how this works, let me show you an geometric explanations how this works. So as I say that we have 2 kind of space. One is a feasible space, the other is an objective space. When we say that objective space, we actually transform all solution into the objective space there. So here, horizontal axis is the F1 and the vertical axis is the F2 there. Now, you see that red line actually the solution pattern on that line. So it might be weak efficient or efficient. So efficient and weak efficient point lies on the red line, and we call this as a Pareto front there. And suppose that we have that this is an objective feasible space. So we have 1 million of points in this feasible space. So what we do, usually we set a reference point to, because as I said at the beginning there, our objective function R is strictly positive. So sometimes it may find that your objective function not strictly positive. In that case, when you add these reference points, maybe set these reference points in such a way so that you force them, the objective function is the functions of which included in the objectives to be strictly positive. So here what we do, we set a reference point in here. We call that utopia point, and we pass a ray. Then, as I say that, we need to choose X set from the feasible set. So when you pass a ray there, we usually run a special linear programming technique there because that's a linear line there. And we find these X set, but there is no requirement that you need to run this, or you need to solve that linear programming problems to find these X set. You can choose any X set from anywhere. Okay, so this is more convenient when you implement your theory into the algorithms. Then you need to find some kind of techniques there, how you can implement your theories into practical purpose there. So what do? We pass a ray there, we choose the X set. So we got an X set. Now, as I say that, we transform our original problem into two subproblems. The first subproblems, let's call it objective function f1 subject to the constraint f2 less than equals to some constraint x2 less than equals to some constant there. So in that case, this one actually, you see it's intersect f1. So here, objective function is f2 subject to the constraint f1 less than equals to some constant. Therefore, you have some new region in here. That's a feasible region. So this is not actually covered the whole feasible space. So you partition there. And similarly, so this is one subproblems. Now try to solve these subproblems. So let's think about it here. So we are trying to minimize the f2, but you have this region only. So what's the point? This point is the minimum point of f2 there. So we got a f2, and we say that these times our solution of this auxiliary problem is x1, and these x1 and x hat both are equal. Now, vice versa, this time I'll set another auxiliary problem. Here, my objective function is f1 subject to the f2 less than equals to constraint. So here what happened, again, you see that this is f2 less than equals to means that only covered this region because you have inequality constraints here. And when you try to minimize the f1, again, you will find these points there. Now, basically, we find that for this particular point, x hat, x1, which is a solution of first auxiliary problem, x2, which is the solution of second auxiliary problems, all three are equal. If all three are equal, you can claim that the point, any point here, because they are equal, the point is the efficient point. Now the question is, if it is not equal, then what you can do? In that case, you can claim that, look, these x1 and x2, they are not equal. So claim that x1 and x2 is not efficient. It may not be efficient, but you can guarantee that those points are weak efficient points there. So that's the way it works there. So this is the geometric interpretation of the proposed scalarization. Now, I'll actually, at the end of my lecture, I'll run my code there, then show you actually how we pass this ray and how we can generate those points, or those weak efficient points or efficient points. Now, that's the geometric intuition. Now, the question is here, can I claim that the solution of this auxiliary problem is the solution of the original problems? So we need to give some theoretical interpretations there. Otherwise, no one can believe you that the solution of your scalarizations is the solution of original problems. So you have to put in some evidence there. So there are two kinds of evidence. You can put it either theoretically or numerically, or if you provide both, then that's a very works well to publish the papers in a very good journals. So here, what was the theoretical evidence? Theoretical evidence say that if you know that X bar is the efficient of an original problem, which I call that P, then X bar also the solution of all subproblem. So that's already proved that. Okay, I'll not cover the proof in here, but I will give you at the end a reference so that anyone can go and check the proof of these theorems there. So basically the theorems say that solution of the original problem, also solution of the auxiliary problems, and the vice versa. Vice versa means that if X bar solves all subproblems, or I can say that if X bar is a solution, is a common solution of all subproblems, then we can claim that X bar is efficient. So this is the important theoretical prospect there. Another aspect there, anyone can raise that, look, it say that, look, if you have 100 objectives there, then you have 100 subproblems. So you need to solve 100 subproblems, then you find a common solution, then you can claim that X bar is efficient. So in a practical point of view, it's a very, annoying there. So you have to spend time there, then you can claim that, okay, this is the common solutions, then claim that that's the original solutions. For some cases, you don't need to solve all 100 problems there. Suppose that if you solve some problems and some subproblems, any subproblems, say that for any k, you solve that, and you find X bar, and this X bar is a unique solution of that subproblems, then you don't need to solve other 99 subproblems there. You can straight away claim that X bar is a solution of the original problems. Or there's a corollary. If you know that your objective functions all are strictly convex, then you don't need to solve all 100 problems. Solve any subproblems there. Then if you got solutions, then claim that, okay, this is the weak efficient point there. So there is a relation between, you need to establish relation between original problems and your new proposed scalarizations. If they have a good relations, then the scalarization works well there. So another theoretical aspect there is a concern. If you see that if you solve two subproblems, if you see the solutions are not same, then what you can do? Is that waste of time? So in that case, no. Our proposed scalation approach is say that if you solve these two subproblems, if they are not equal, if they are not the same solutions, then say that I can't claim that this is efficient, but I can guarantee that this is a weak efficient point. So that's the theorem actually says that. Okay, then the converse of this theorem is not true. For example, I can set some counter examples here to prove that the converse not true. Say that if you say that some weak efficient point, can you guarantee that weak efficient point as the solution of any subproblems or solution of all subproblems? No, we can't guarantee that. So if you see that here, these examples, we have three objective functions. The first objective function is x plus 1 whole square plus 1. Then the second one, x plus 2 whole square plus 1, then 4. So we have three objectives here. The last one is a constant function there. And here, definitely we can claim, we can see that x bar equals to 0 is a weak efficient solutions, because we will not find any x which is clearly dominated with these solutions here. And the constraints, look at the constraints. The constraint is a -4 to 0 there. Now, choose some w, say the w1, if I set some w1, w2, w3, so what do I mean there? Look, when you set a counter examples, you don't need to show these problem holds for all of them. You just say that for this particular case, this is not whole, therefore the theorem violates there. So here we choose some particular weights there, and we see that we create a subproblems where f1 considered as objective, force other two objective functions into the constraints there. We solve these subproblems, and as I say that we claim that the x bar is efficient solutions. However, we know that x bar is not an optimal solution of P and x1 hat, because our constraint is -4 to 0. So you can still choose -4 as a solution. So x bar is not a solution in here. So it means that the opposite, the vice versa, doesn't true, so not holds there. Only you can claim that if x bar solves for some k, say that if x bar solves some auxiliary problems, then you can guarantee that the x bar is a weak efficient point. Now next, when you set some scalation approach, we often set some criteria. Or when you propose some algorithms to solve some problem, you need to set some criteria. in which basis you can claim that this algorithm is better. So in that case, we set 3 conditions there. Say that the method, whatever we propose, the method should approximate the true boundary of the Pareto front. So what is the true boundary? Is actually the exact boundary of the front. So the method should approximate the boundary of the Pareto front, and the method should take less computational time, because computational times, if it takes more, then it's a very disadvantage of the algorithms there. So you need to keep these less computational times, and you need to generate Pareto points as evenly as possible on the front. So our experiment shows that the proposed algorithm actually has a strength, or has fulfilled all these 3 criteria there. Now, let's take an examples, then see how this works. So before showing the examples, I need to give you some kind of descriptions of how you provide those grid points there. So grid points, as I say that I consider these as a W, capital W in my slides there. So these are the grid points you need to provide into the algorithms. Then for those grid points, you need to solve these auxiliary subproblems there. Okay. Now, is that possible to provide any grid points into the algorithms? No, there are some criteria how to choose those grid points. So one of the criteria is a very famous criteria. They call the Das and Dennis criteria for providing grids. So it has a name. It's called a CHIM grids. CHIM actually abbreviation is a convex hull of individual minima. So what do we do? First, suppose that this is the Pareto front. You need to find these points. So this is actually the optimum point of F2. And choose another point, just the optimum point F1. Then draw this line, then evenly partition this, and select a reference point, pass a row through those partitions there. So this is a very common base points. So you have a common base points. Sorry. We have a common base points in here, and we have different, partitions there. So directions are different here, but the base points are common. Or you can choose different base points, but the directions are same. So whatever it is, so these are the techniques you need to provide parameters into the algorithm. So you need to consider those there, because at the end, your Pareto fronts or efficient point depends on these grids there. So you have to be careful when you choose those grid points for the algorithms. So another grid points, these actually, so this is a CHIM grids for the 3-dimensional space. You see that all the grids evenly distributed there. So those are the parameters. And now I'll force those parameters into the algorithms. Now, another grid points, this works when the objective function is more than 2, because there are some things there. For example, if you have a surface, you see that some of these boundary lines should be curved. If you just think about the sphere, the boundary line should be a sphere, so should be the curve there when you consider that it's not a straight line. So in that case, Das and Dennis grid points sometimes actually miss those Pareto points, which actually outside this line there. So therefore, another grid points, actually, they introduced Moyla-Grischenier in 2009, the paper published from SIAM, who actually choose the individual performance minima. That means that find the individual solution of each of the objective function, locate that, then compare F1 and F2, F2 and F3, F3 and F2. So find the only boundary point like that. So once you have the boundary, you see that boundary, if you just add these 2 green circles there, you will find a straight line. Now this looks a curve there. So if I follow the Das and Dennis, it means that some of the points that outside this straight line, joining this straight line, so if you consider these 2 joining line there, those points, red dots, is outside those lines. So in that case, I can miss those Pareto points, which actually the outside of that line. So when we follow the essay grid points, we can generate the boundary, exact boundary of the front. Then After that, if we do some kind of linear scalation techniques to generate the inner points there, something like that. You see that star, they are inner points. So it's a step by step. First, in the first step, generate generate the individual performance minima. That means a solution of each of the observing function, then generate the boundary, then generate the inner points there. So these actually, basically, I show you that somebody else actually gives some criteria to generate the grid points. What do we need? We need those ideas because we want to show that our proposed scalation approach works well. So in that case, we need to make sure that we are providing a very good grids into the algorithms there. Now, let's take an example. This example, you see that I created these examples. So this is the first one is a sphere there, some inequalities, and second one is some kind of paraboloid inside so that I can make it more complicated, the algorithm. Sometimes what happens, if the examples is easy, then you can see that all algorithm actually works well. But
Dr. Rizvi,
yeah,
can I
yes,
can
yes,
you finish
please.
within 5 minutes, please?
Yeah, yes, I'll do that. Awesome. Thank you. Then there are some, definitely we set some criteria. You see that because of time limitations, I will not explain these tables here. Now I'll show you the experiment results. So what happened? This is for Pascalotti Serafini approaches there. You see that the blue line, they are actually true boundary points, but somehow it needs to generate those points there. For PKW, again, you see that the blue line is not generated by the algorithms. Here, Das and Dennis is actually what happened. You see that the point like a triangle shape, it actually what happened. Sometimes you may find some bad points there. So there are some filtering techniques. You can apply those filtering techniques and you can get rid of those bad points. So those bad points not comes for the scalation approach. It comes from the solver that you are using there in the algorithm. So here we can see that these MPS is worse results there because some of the points, even though we are filtered, is not actually weeded out or removed from the paragraph. So this is the approach. You see that how nicely generated each of the boundary and inner boundary of the fronts. So that's actually for our proposed scalation approach. Again, so this apply chim grid. Now, what about essay grid? When you, again, there are some table there. So if anyone wants, then I can send my slides there so that you can see the statistics of the algorithm. So here I provide the essay grids there. When we provide the essay grids there, again, you see that our proposed algorithms actually works well. In that case, we can see yellow. Yellow means that they are bad points. They comes for the solver, but yellow indicates that we can able to filter those 2 points there, and more yellow in there. And green means that even the filtering, we can't remove those from the front. Now, you see that another examples, again, I use the chim grids. Again, this is the works, is the better result found for our proposed scalation approach. And this is when I provide chim grids. When I provide essay grids, looks like that. So don't think that there's a corner actually, so don't run away. And it's actually the experiments done 3 years ago. So this is another examples that where we can claim that our algorithm works well. And at the end, I don't have time, so I'll just quick go through the rocket injector design problem. So what we did at the end, we tried to implement our proposed techniques into the real life application. So in that case, we choose a 4 objective optimization problems. So this is actually called rocket injector design problems. In 2004 and 2006, Goel and Buddhanathan, they worked for NASA. They model these algorithms. So it has a 4 objective functions and 4 variables there, and they model the functions. So we don't have any contributions to model these functions. However, we choose this. Actually, we want to check how works well our proposed algorithms there. So you see that that's the results actually Buddhanathan and Goel found during their project, NASA projects there. They say that, look, even though they have 4 observatives, they can say that F1 and F3, they collide. They are very close to each other, then they ignore one objective functions, then they convert these to 3 objective functions, then they solve the problem. They say that that's the actual boundary of the Pareto front. Now we say that in our algorithm, we say that no, we can't ignore other objective functions there. So that's, we consider all 4 objectives. So this is the projection of F1, F2, F3, same projections that actually NASA guys, they consider. We say that some of the part is missing in here. So we claim that these algorithm, if someone else, this algorithm used, they may find a better Pareto front for the multi-objective optimization problems. So these are the reference, key reference. So one of the reference is the Pascalotti-Seraponi, as I said, at 1994 is a paper of Journal Optimization Theory and Applications. So Das and Dennis from SIAM journals, and we published a paper that that actually not presented in here, is a Journal of Optimizations. Also, we used, they included the result of this scalarization approach. That's why I included this reference in here. Now, Moyler-Grishner, again, this is a very, very well-known paper for the grid generations. It's appeared from SIAM. Badhanathan and Goel, as I said, that these NASA guys, their paper appeared in here. And the results that I throw actually explained our proposed algorithms. The result actually published from SIAM Journal on Optimization in 2007. That's a joint collaboration work with Rahina Hurachik and me. And what else? So at the end, as I say that, I want to show you that how these algorithms works. I'll take only 1 minute there. So what we do, as I say that we need to choose some reference points. So we need to write code in MATLAB. And when you run the algorithms, you'll see you need to pass array. So in that case, it's a different base point with the same directions. And when you pass array, it just generates the Pareto fronts there. So those are actually efficient points. So whatever it is in our proposed algorithms, it's not guaranteed the efficient points. Weak efficient points and efficient points, anyone's is there. So that's the way we actually implement the algorithms. So here, thank you all for your, thank you very much for your attention and for your valuable time. Yeah.
Okay, thank you, Dr. Mustafa Rizvi Bhai, for your nice presentation. So I'm searching some question from our valuable audience. Please ask some question if you have. Or okay, so if you any have further query or any kind of information or searching some problems, you may directly contact with Dr. Rizvi. We have his email and he's available for us also. Okay, so this is the end of our scientific session. So please, screen share of Professor Rizvi. Okay, please. Okay, so now I'm requesting Irfanul Kobir Chaudhary to give a token of appreciation to Dr. Mustafa Rizvi. He's so far from us, don't worry. So on behalf of you, your family will receive your crest. So this is our duty. This is our responsibility to send this crest to your family. And we are very
thank you. And
you.
I have a question. Is that gold?
No.
That's great. Okay, thank you.
Okay, thank you very much.
That's good. Thank you. Thank you for your grace.
Yeah. So this ends our first session. So now we are going to our second part, that is the discussion session. So now the time is very short and we are very grateful to our respectable professor, respectable teachers who are long time staying with us. So now I'm requesting Professor Dr. Neil Ratan Bhattacharya sir to say some few words to us. Professor Neil Ratan Bhattacharya sir. Sir is available or? Requesting Professor Neil Ratan Bhattacharya sir. Sir, are you available? Okay, maybe sir is not here. And now I'm requesting our respectable professor, Professor Ganesh Chandra Rai. Sir, we have for the first time we are arranging a such types of conference to celebrate the International Day of Mathematics is very new. So we are trying. So maybe in the next time or within after 3 or 4 months, we'll arranging such a seminar. So, sir, can you advise or tell something or discuss something about today's seminar? I'm requesting Professor Ganesh Chandra Rai. So say some few words.
Hello,
Yes, sir.
can you hear me?
Yeah, it's clear. It's clear, sir.
Clear? Okay.
Yeah, sir, clear.
Okay.
We can
So
see you
I
and
have
hear you.
just few words. Thank you inviting me to join this seminar. I appreciate the department's initiative to celebrate this day. And I want to say thanks to all presenters who presented their research papers in this seminar. But I think as this day is Mathematics Day, International Mathematics Day, so I thought that instead of these serious papers, in my view, it was more fruitful if we have the discussion popular topics in mathematics. This is my view about this seminar. And also, I have the second comments on this, that we have taken so many times to present 40 minutes minimum. So I thought that participants as attending in the Zoom was not so attentive. And I thought it should be was 20 minutes per presentation. And all the presenters who has given their research papers, it should be talk like introduction to the topics, that what you want to discuss and what was already done, and next development of the researcher, that is what he have done in this respect. So these two suggestions for me. And I don't know how many participants were in the Zoom meeting. Dr. Amanullah,
So
can
initially
you?
Initially it was 125.
Now
Around 60.
Yeah, now
it is difficult to say. Okay.
60.
So
yeah.
I think, as I have talked, that it was more fruitful if we can talk with popular topics and time minimum of 20 minutes, maximum of 20 minutes for the presentators. Then all the participants, I think, can enjoy it more. Because in meantime, I am also taking tea and other thing. I am doing also jobs, because to hear this type of presentation was good, but it is difficult to catch all the things from the researchers as we are in a distance. If it is in the room, we can see the their presentation more and more, and we can able to talk something about this. So I thought this is my observation, and I want to say thank you all, and especially thanks to all presenters in this seminar. Okay, thank you, Dr. Raman.
Thank you, sir. We will follow your suggestion in near future. Thank you, sir. So now I would like to Professor Musliuddin, sir, to say some few words for us. Sir is available. Professor Musliuddin, sir, can you hear me? Maybe sir is went out. Anyway, so now I would like to request our more respectable Professor Abul Mansur Chowdhury, ex-director, Jama Nuzrul Islam RCMPS, and the UGC professor. So now I would like to request Professor Abul Mansur Chowdhury, sir, to say some few words for us.
Where I am, I don't know now.
Sir, we can hear you, no problem, sir.
Where are you now?
Sir, we cannot see you. Can you open your video, please?
That's what I'm saying, trying to do. But where are you now? Let me talk because
Yeah.
I cannot.
Yeah. Okay, sir. No problem.
Okay, thank you all for inviting me to this nice conference on a special day. Well, I am very grateful actually to all of you for inviting me to attend this conference and to say something. You know, these types of conference is always very important. And today is a special day for mathematicians because the UNESCO declared this day the International Day of Mathematics. So any organization come across with some types of special seminar, conferences or competition, it will be fruitful for all of us. This day is mainly for taking awareness about the importance of mathematics to encourage our students, fellow colleagues, and everybody. So we are very proud that mathematics is used in science, you know, all of you. But nowadays, I think because its wide application is not limited to only mathematics in science.
Mansur sir, we are not hearing properly.
Not hearing well. I
স্যার এখন ক্লিয়ার স্যার, এখন ক্লিয়ার স্যার। ওই মাইকটা একটু মুখের কাছে নিলে হবে স্যার।
এখন
স্যার ক্লিয়ার, স্যার ক্লিয়ার।
Now good.
Well, it was in the science, but nowadays people already understand that it is not only the queen but king also. But language, I say it is not king and queen, but it is a language. Only language. It is a very powerful language because through it we can express anything very clearly. I don't know why I am saying this is powerful, because we can go from 0 to infinity. No language can go from 0 to infinity, but mathematics can go from 0 to infinity. We can enrich our domain from finite to infinite. So, our mathematics is very advanced, and that's why we are very proud that we are mathematician. We are member of the family of the mathematics. So now in these conferences and any competition, we encourage our students, as Professor Ganesh has said, that to encourage our students to make it short, because papers will this is a very concrete paper, and you have to have a specialization on that field, otherwise you cannot understand.
Yes, yes.
Let me say, three speakers actually they are very good. Let me say, Professor Islam, he talk about tensor analysis. If he said about the application of the tensor, that would be more fruitful to us. What is the application of the tensor? What we are doing? What is tensor? He accommodated the tensor. He analyzed the algebraical analysis of the tensor. But
this is lengthy, yes.
You see, when we got the Einstein's equation. What is this? That is tensor. So tensor got this idea that he got this Nobel equation which created from which you can find anything. So applied tensor is that. And when you can apply the tensor, it is on curved space, not on linear, not on flat space. It is on curved. Tensor is on application of linear curved space. That is Riemannian geometry. If he talk about these things, that would be more fruitful to our students. And he said something about the application of mathematics very good, nicely in the beginning. Later on, that there is one thing that she should mention, that the application of neighbor equation. That our, Mr. Mahabub, I think he asked about the neighbor equation. So he should say this is the application of neighbor equation, which is the most important equation in fluid mechanics. That the application of this under these conditions, that they will understand what is the neighbor equation and what is the importance of it, and how we can use it in fluid motion. He is a good lecturer. He did very good thing, but he said the application of the optimization problems. You know, today's world, it is a very hard problem. The optimization problem.
দাদা তুই একটু শুইতে পারতি, তোর ঘুম আসছে কিন্তু এখানে এই কাম হিয়ার এখানে
very nice, but he should again he some application where we are using this thing. But these problems are mathematical problem, but where we can use it. If he shows this thing very nicely, then it will be very more. Without going to the theory and going to the application. This is a very good thing that the Department of Mathematics started conference like this, and we'll be very glad to hear from in future. I'd like to thank every today's participants, and also especially Professor Musliuddin Ahmad, Professor Nashai, Professor Ninot Masaji, Professor Arshad Islam, and others. I welcome you all again in future. And all of you will be with good condition in this pandemic situation. Today, thank you.
Thank you, sir, for your nice speech. Actually, today we are missing our respectable colleague, Professor Shafil Alam Tarabdar. We pay our respects to Professor Shafil Alam Tarabdar, and we pray to Almighty for the departed soul. So now we are very glad to inform you that our Professor Musliuddin sir already joined with us. So now I would like to request Professor Musliuddin sir to say some few words for us. Sir, can you hear me? Sir Musliuddin sir, please say something for us.
ওখানে যায় মাথা দিয়ে শুয়ে পড়ো, এই যে এখানে পড়ে গেছে এটা।
Sir, can you hear me? I'm talking with Professor Musliuddin sir. Musliuddin sir তো আছেন।
মুসলিউদ্দিন স্যারকে আনমিউট করে বলতে হবে।
হ্যাঁ স্যার, একটু আনমিউট করেন, স্যার একটু আনমিউট করেন, স্যার একটু, স্যারকে দেখলাম কোথায় আছে তো। Sir, we cannot hear you. স্যার তো জয়েন করলো দেখলাম। ইরফান স্যার আছে না?
হ্যাঁ স্যার আছেন, স্যার কথা বলছেন তো, কিন্তু বাট শোনা যাচ্ছে না।
স্যার আনমিউট ইওর ফোন স্যার।
আনমিউট আছেন?
আনমিউট করা আছে এখন স্যার, বাট স্যারের ভয়েস আসতেছে না, মনে হয় ইনপুট স্পিকারে একটু প্রবলেম করতেছে।
আচ্ছেন ওই তো স্যারকে ভিডিওতে দেখা যাচ্ছে তো।
হ্যাঁ দেখা যাচ্ছে।
হ্যাঁ স্যার কথা বলতেছেন কিন্তু আমরা শুনতে পাচ্ছি না।
আমি তো স্যারকে দেখতেই পাচ্ছি।
আমার এখন দেখা যাচ্ছে নাকি?
হ্যাঁ স্যার এখন দেখা যাচ্ছে।
আমি এখন বাইরে আবার ঢুকছি যে।
এই ইরফান স্যারকে দেখতে পাচ্ছ, একটু নক করো না।
স্যার আছেন তো, স্যার তো এখন আমাদের কথা শুনছেন না মনে হয়। আমরা
তার মানে উনি মনে হয় আনমিউট হয়ে আছে।
না স্যার মিউটে
উনি আছে, কিন্তু স্যারের মনে হয় কথাগুলো স্পিকারে আসছে না, কম্পিউটার আসছে না, যার কারণে আমরা শুনতে পাচ্ছি না।
মুসলিউদ্দিন স্যারের সব এবং মিউট করবে।
হ্যাঁ হ্যাঁ আলিম ভাই, কি স্যারের কথা তো শুনতে পাচ্ছি না।
আমান ভাই আপনি তো হোস্ট হিসেবে কিন্তু আনমিউট করে দিতে পারেন।
আমি তো স্যারকে খুঁজে পাচ্ছি না। স্যার পাইছি তো না, স্যার তো অলরেডি।
স্যার তো আনমিউট করা আছে অলরেডি।
তাহলে স্যারের মাইক্রোফোনের সমস্যা মনে হয়। তাহলে
মাইক্রোফোনে ইনপুটের সমস্যা স্যারের।
স্যার আপনি মাইক্রোফোন নিয়ে ফেলে শুধু ডাইরেক্ট কম্পিউটার থেকে কথা বলেন মুসলিউদ্দিন স্যার। মানে মাইক্রোফোনটা খুলে ফেলে সরাসরি কম্পিউটার থেকে কথা বললে শোনা যাবে।
হ্যালো স্যার, আমাকে শুনতে পাচ্ছেন? মুসলিউদ্দিন স্যারকে বলছিলাম, স্যার আমরা আপনাকে শুনতে পাচ্ছি না।
স্যারকে রিং দিয়ে বলো, ফোন দিয়ে বলো।
হ্যালো
শুনতে পাচ্ছ?
হ্যালো
হ্যালো
স্যার শুনতে পাচ্ছি।
এখন শুনতে পাচ্ছেন?
স্যার ওকে 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 স্যার এখন ক্লিয়ার।
Yeah, I hear you.
Yeah, sir, and now is clear. Sir, now is clear.
Yeah.
Sir, you can say something.
Yeah. Okay. Well, I am very happy that you guys organized such a seminar at this corona crisis, and you know, it is very, very encouraging, and you keep doing it, you know. And I remember on this day, this is the 14th March, you know, that this is the birthday of Einstein.
Yeah.
And I remember my reverend teacher, respected teacher, Professor Jamal Nazrul Islam. I went to the hospital on the 15th March, and I was not allowed to see him because he was in intensive care. So I wrote a message, and then I told him this, that I remember this 14th yesterday, 14th March, Einstein's birthday, and on this day I arranged the thesis defense for me, because it was arranged on the day before, and that means on the 13th. Then he smiled at that time and said, "Okay, no problem." Then I took that exam. I mean, the thesis defense. And on that very night, at dead of night, maybe I don't remember exactly, maybe 2 o'clock, and Shaheen called me at dead of night, and she said that Professor Jamal Nazrul Islam passed away. Well, these are the things that I remember about this day. And since this is the first time you are arranging International Mathematics Day, if you arrange it next year, you guys let us know, ahead of time, so that we can also participate actively. Well, I wish you everybody here, Dr. Aman, Ashraf, Dr. Ashraf, Dr. Jalal, you people worked very hard, and I wish you again success, and may Allah bless you all. Thank you.
Thank you, sir. I am very grateful to our seminar arranging committee, because department also make a committee which is headed by me and Professor Jalal and Irfan Al-Kabir Chaudhary. And I'm very grateful to all of our colleagues, especially Department of Mathematics, all teachers who are helping us to arrange this seminar. And we hope that in near future, we will arrange such types of seminar or conference in a big way. And of course, it will be offline, not online, because due to this pandemic situation, we are arranging this conference in online. So now it is the concluding session. So now the open floor. So to our colleagues, will you say something? If our colleague is wish to say something, then please, from our colleagues, our departmental colleagues. So if you want to say something, so this is the time for you. The floor is yours. For our departmental colleagues, can you say something, or we will go for the end session, and the concluding session will be declared by our chairman, Professor Dr. Nurun Nahar Begum. So I think nobody can say something, and we are almost 3 hours. So now I'm requesting Professor Dr. Nurun Nahar Begum to concluding the session. Actually, we are trying our level best, and if any kind of mistakes, please forgive us. And maybe in future, we will follow our respectable the teacher's recommendation, and maybe we will arrange in a big form. So now I'm requesting Professor Nurun Nahar Begum to conclude the session. Please.
Thank you very much. I thanks the delivered nice papers, and our teachers, that is Sir, Mansur Sir, Musliuddin Sir, Ganesh Da, who said in this session, everybody, I welcome them. And thank you very much. Now, all the participants also, thanks. It is very sad that participants are no more now. Okay, I am now closing the session. I declared that Professor Aman Ullah will close the session.
Okay, madam, thank you. Thank you very much. And we are very glad to inform that from Canada, Mr. Mahabub Rahman also joined with us. Abdullah Mahabub from Kumilla University, Associate Professor, he also joined with us, and also many more renowned our ex-students also join with us, and we hope that in future, maybe they will directly join with us. So in this sense, this session, and today we are going to end, and respects, and we are very glad to our respectable teacher. We hope that Professor Mansur Sir, Professor Musliuddin Sir, and Professor Ganesh Chandra Sir stay with us if in future we will arranging any kind of programs. Thank you, sir. Thank you very much.
Thank you. Very good day.
Thank you.
Thank you all.
Yes, sir. Assalamualaikum.
ফোরকান, অনেক ধন্যবাদ, কষ্ট করে জয়েন করেছো ফোরকান। অনেক ধন্যবাদ, খুব ভালো লাগতেছে অনেকদিন পরে। এই আব্দুল্লাহ মাহবুব,
থ্যাংক ইউ স্যার।
কি অবস্থা? তুমি তো অনেক ধন্যবাদ, কষ্ট করে আমাদের সাথে এতক্ষণ ছিলে। আমরা আসলে মানে এবার আমাদের মধ্যে থেকেই দিলাম, তো হয়তো নেক্সট টাইম আমরা আরো একটু বড় কিছু। এই লিপন তুমি আসো, লিপন তুমি আসো।
থ্যাংক ইউ স্যার। আসি স্যার। ভালো আছেন স্যার?
হ্যাঁ মাইনুদ্দিন, তুমি কোন জায়গায়, চিটগং না রাজশাহী? আচ্ছা আচ্ছা আচ্ছা, অনেক ধন্যবাদ, অনেক ধন্যবাদ। না আমরা জাস্ট এমনি করলাম আর কি, কারণ এবার শুরু করলাম তো, হয়তো নেক্সট টাইম বা অন্য কোনো 3-4 মাস পরে
আচ্ছা, খুবই সুন্দর হয়েছে স্যার, খুব ভালো হয়েছে।
আয়োজন করব আর কি। ওকে তাহলে থ্যাংক ইউ ভেরি মাচ। হ্যাঁ ওরকান, ভালো থাকো।
Thank you all
আব্দুল্লাহ মাহবুব,
for arranging this.
দাওয়াত রইলো।
such kind of
শ্বশুর বাড়ি আসলে হবে না, একটু ডিপার্টমেন্টের চেহারা দেখাইতে হবে। আর মাহবুব কানাডা, ওর তো অনেক রাত, বলছিল বলে স্যার আমার 3টা বাজে, তারপরেও ও ছিল। ও আল্লাহ, তুমি নেই মাহবুব?
না আমি আসলে আমাদের এখানে ডে লাইট সেভিং হয়েছে তো, যার ফলে আমি চান্স পাইছি আর কি জয়েন করার।
আচ্ছা 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 আচ্ছা, অনেক ধন্যবাদ।
ফজর নামাজ পড়ে তারপর দেখলাম যে আপনারা আছেন এখনো, তো জয়েন করলাম।
অনেক ধন্যবাদ।
তো দোয়া করবেন সবাই আমার জন্য।
হ্যাঁ হ্যাঁ, দোয়া রইল সবার জন্য।
আচ্ছা স্যার, ভালো থাকবেন স্যার। স্যার আসসালামু আলাইকুম।